In section 4.3, and we're going to talk about right angle trig.
So this is like review.
It's more or less review, yes. So I want to draw a right triangle, and we'll label our sides, and we'll talk about our, is that the way I want it? Yes. Let me make that a little bigger. There we go. All right, so we're back to talking about triangles. We're not talking about wrapping our number line around our circle today. We'll get back to that in just a little bit. So we're talking about triangles. So all the angles that we're talking about are going to be acute angles. So we're talking about angles between 0 and 90. And we're going to label the sides of our triangle. So the long side across from the right angle is our hypotenuse, our adjacent side, and our opposite side. So back to SOHCAHTOA. So sine theta. Sine theta is opposite over hypotenuse. Cosine theta, adjacent over hypotenuse. And tangent theta is opposite over adjacent. And then we can do our reciprocal functions, the cosecant, hypotenuse over opposite. And what's another way we can think of the cosecant? Reciprocal of this or the reciprocal of this. They're both the same thing. The secant of theta is the hypotenuse over the adjacent, or 1 over cosine theta. And then our cotangent is adjacent over opposite, and that's the same as 1 over tangent theta. So these are our basic, our right angle, we call them our trig, 6 basic trig ratios. SOHCAHTOA, we could think of them as SOHCAHTOA. So what I want to do is talk, briefly related back to the unit circle, and then we'll do a couple of examples using this stuff. So let's draw a 45, 45, 90 triangle and label the sides and use these things and relate what we're doing with a right triangle to what we talked about with the unit circle. So here is my 45, 45, 90 triangle. And those are my 45-degree angles. And if this hypotenuse is 1, each of those sides turns out to be square root of 2 over 2. And if we didn't know that, we could say this hypotenuse was 1, call each of these sides x, use the Pythagorean theorem, and figure out that each of those sides has to be the square root of 2 over 2 if the hypotenuse is 1. So, and no matter how big or how small our 45, 45, 90 triangle is, these proportions between the sides are always going to be true, because 45, 45, 90 triangles, no matter how big or small, are all similar. So all their sides are going to have the same proportions. So let's talk about our trig functions of 45 degrees. Sine of 45 is sine is opposite over hypotenuse, square root of 2 over 2, just like we talked about on the unit circle. Our cosine 45 degrees adjacent over hypotenuse, also square root of 2 over 2. And then the tangent of 45 is adjacent, opposite over adjacent, 1. So thinking about the x and the y coordinates on the unit circle, it actually came from using this 45, 45, 90 triangle, but we come to the same place if we talk about it with SOHCAHTOA. All right, let's draw a 30, 60, 90 triangle. So there's my right angle, my 30-degree angle, my 60-degree angle. We're going to say the hypotenuse is 1, just to make our lives easy. On a 30, 60, 90 triangle, the short side is always half the length of a hypotenuse, and the long side is always square root of 3 times the length of the short side. So that gives us square root of 3 over 2. If we couldn't remember why that worked, a 30, 60, 90 triangle is half of an equilateral triangle. So this side is half the whole side of the triangle. And then we can use a Pythagorean theorem to find that piece right up the middle of the equilateral triangle if we drew the second half in there. The 30, 60, 90 triangle is half of an equilateral, and that's how you can come up with these relationships between the sides. And this is always going to be the case in a 30, 60, 90 triangle. The sides are always going to have this proportion. Short side's half the hypotenuse, and the long side is square root of 3 times the length of the short side. Always going to be the case in a 30, 60, 90. So let's find our sine, cosine, and tangent of our angles here. So sine of 30 degrees. Opposite over hypotenuse, 1/2. Cosine of 30 degrees, adjacent over hypotenuse, square root of 3 over 2. Tangent 30 degrees is opposite over adjacent, 1/2 over square root of 3 over 2. And that, how do we simplify that? Divide by a fraction, we do what with it? Multiply by the reciprocal, the 2's cancel. I get 1 over the square root of 3, and that simplifies to square root of 3 over 3. Multiply the numerator and denominator by the square root of 3. So if you can't remember what the tangent of 30 degrees is, you can always go back to this ratio and then simplify. And I'm just going to erase this and put our answer in there. All right, let's do our 60-degree angle. Sine of 60 degrees. So opposite over hypotenuse, square root of 3 over 2. Cosine 60 degrees, adjacent over hypotenuse, 1/2. And tangent is 60 degrees. Opposite over adjacent, what are we going to get there? Square root of 3 over 2 divided by 1/2. Square root of 3. Do you see any relationship between these two? These are the same? These are the same? And how are 30 and 60 degrees related? They are what kind of angles? What is this, Stephanie? They're complementary. 30 degrees and 60 degrees are complementary. That turns out to be true for any pair of complementary angles. The sine of an angle is the cosine of its complement. And that's because you set it up in this triangle like this. The sides when you look at the complement of the angle in a right triangle, it's the other angle in that right triangle, so the opposite and the adjacent side switch around. So what the side that's opposite the 60-degree angle is adjacent to the 30-degree angle, so they switch around. So with complementary angles, that relationship's always going to be true. The sine of the angle is the cosine of the complement. So the way we write that is for complementary angles. The way we write that is that the cosine, let's start with sine. Sine of 90 degrees minus theta equals the cosine of theta. The cosine of the angle equals the sine of the complement. To find the complement, we subtract from 90 degrees. And I can say for the cosine, 90 degrees minus theta equals the sine of theta. We can do the same thing for tangent. Tangent of 90 degrees minus theta is the cotangent of theta, the cofunction. We can do the same thing for the secant and the cosecant. And I can do these in both directions. So I'm just going to do dot, 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 because we can do it for each pair of cofunctions. Sine, cosine, tangent, cotangent, secant, cosecant, and it can go either direction. So if we find the complement of one, that's going to be the cofunction of the angle for the other. So cosine of the angle is a sine of the complement. Sine of the angle is a cosine of the complement, etc., etc. Works for every pair of cofunctions. So sometimes this can help us solve problems. We'll end up with some problem where we have a 90 degrees minus theta or a pi over 2 minus theta. We can replace that with just the cofunction of the angle. All right, questions there? All right, I just want to look at a couple of examples before we're done. Easy examples. These should be easy. Pretty standard right angle trig questions. Let's say we have the sun is up 30 degrees from the horizon. And we have a tree with a 25-foot shadow. How tall is the tree? Thanks, Chris. So what I always suggest to do on these is draw a picture. Picture can help you, and they're also fun to draw. So there's my sun. And here's my tree. I guess if it was really hot, we could draw the sun. The sun would look like this. And then you'd be worried about getting the sunburn. I would anyway. And it says the shadow is 25 feet. So the shadow goes to here. And we're assuming that this is a 90-degree angle. And it says the sun is up 30 degrees from the horizon. I didn't draw my picture really well. So that's telling me that this angle, and I need to draw my shadow a little longer. There we go. So this is 25 feet, and this angle is 30 degrees. And it wants to know how tall the tree is. So how are we going to solve this problem? What sides of our here's our angle. What sides of our triangle do we have? Hmm? All right, so we say the tangent of 30 degrees is the opposite over adjacent, x over 25. So x equals 25 tangent 30. And didn't we just figure out what tangent of 30 degrees was? Square root of 3 over 3. So that would be our exact answer. 25 square root of 3 over 3 feet. And we could find an approximate answer. So x is approximately, plug that in the calculator and calculate. I don't have that calculated out. So we could plug it into our calculator and calculate that to get an approximate answer.
Most of the problem we do is just going to be put it both down.
Unless it's a unit circle angle that we know, then it's going to be a calculator problem. You just have to plug it into your calculator. So because we knew this one, we happen to know this one, we could put an exact answer. And I think I forgot to mention at the beginning, with triangles, you're almost always going to be working in degrees rather than radians. So in triangles, we're working in degrees. Okay, let's look at another example. So we have a flagpole. This could be the one that the mathematician found the height of for the engineers. So we have a rope at the top of a flagpole. And our rope is 35 feet long. And it's attached 25 feet from the pole. We want to know what angle the rope makes with the ground. So here's my picture, here's my rope tied to the very top of the flagpole. It's 35 feet long. It's attached here with this big stake, 25 feet from the flagpole. Here's my flag. And we want to know the angle that the rope makes with the ground. So what are we going to do here? We're assuming that this flagpole is 90 degrees, is vertical, nice straight flagpole. So what someone said, what do we use? Cosine. So we're going to say, because we have the adjacent side and the hypotenuse, cosine theta is 25 over 35. And if I have the ratio, if I have this piece, how do I find the angle from that? Theta equals, how do we get the angle from our ratio? The inverse cosine. Cosine to the -1. Inverse cosine of 25 over 35. So this is when we use the inverse cosine button. This is when we want to find the angle. Inverse cosine gives us an angle. If your calculator is in degree mode, your inverse trig functions are going to give you angles in degrees. If your calculator is in radian mode, your calculator is going to give you the angles in radians when you use the inverse trig function. So I plug this into my calculator, and I get that this is approximately 44.4 degrees. For triangles, you almost always use degrees. I would say, I don't want to say always, because when you say always you get in trouble, but almost always with triangles you're going to be in degrees. Otherwise we're going to be using mostly radians. All right, let's look at one last example. So for this one, we want to find exact values for the 6 trig functions for theta. And we have a triangle here. So we're going to say here's theta. We're going to say this side is 8 and this side is 15. So exact value means we are not using our calculator. We're writing these as fractions or something like that. So we want our exact values. Now, a lot of students, after we've talked about the unit circle, a lot of students make the mistake and they say, okay, this piece, because it's the horizontal piece, well, that's the cosine, because we said the cosine was the x-coordinate, and this piece, this number is the sine, because we said the sine is the y-coordinate. Why can't we do that? It's not necessarily that way, so this is just how we happen to draw it. And what else are we missing here? What's true always on the unit circle? The radius is 1, so the hypotenuse is 1. This hypotenuse is not necessarily 1. And our trig ratios have a hypotenuse involved. So on the unit circle we can simplify things because our hypotenuse is 1. And we also, that gives us an orientation for our triangle. So, but we don't have the hypotenuse. We're stuck. We can't do this problem. Right? Pythagorean theorem. Pythagorean theorem always works. Pythagorean theorem is our best friend when it comes to right triangles, because it always works. When you see a right triangle, the first thing you should think is Pythagorean theorem. The second thing you should think is trigonometry. And the third thing you should think is I love triangles. So we can do the Pythagorean theorem. Let's call that C. Maybe that should be the first thing you think is I love triangles. And then the other things. C squared equals 15 squared plus 8 squared. So C squared equals 225 plus 64. So C squared equals 289. Anybody know the square root of 289? Perfect square? 17. C equals 17. So that's one of our perfect squares. So this is a Pythagorean triple. 8, 15, 17 is a Pythagorean triple. Alright, so now we're set. C equals 17, and we can write all of our 6, the exact values. So, for example, I'm not going to write all 6 of them. Sine theta is opposite over hypotenuse. 15 17ths. Cosine theta, adjacent over hypotenuse. 8 17ths. And I could keep going that way. The cosecant would be the reciprocal of this. The secant would be the reciprocal of that. The tangent I can find using my triangle. Go from there. All right, questions there? All right. There you go.